when did the Big Bang happen? How do we begin to estimate the age of the universe? So how do we know how old the universe is at all? I mean, this is an extreme concept, okay? This is a question that you could argue that humanity has been asking itself since there were humans to look up in the sky and think about things like this. How long have we been here? How old is the universe? Has it always been, or is the universe changing and evolving with time? So as we talked about with the discovery of Hubble and then subsequent observations from that time, there's this indication that the universe is expanding. And what that means is not just that it's expanding, but that it's changing with time, that the universe is not today as it was long ago. Okay? And that's a qualitatively different picture of the universe than many people had before this discovery. It's not an ever-present universe that's always been the same forever, eternally. But it's actually evolving with time. Okay? So we have this picture where the universe is expanding out like this. And the way we describe it mathematically is with Hubble's law, that the velocity of different distant objects are correlated with the distance to those objects. The farther the objects are away, faster they're moving away from us. Now, so if you have a universe that looks like this, that's expanding, you can imagine running that movie backwards in time. Okay? So at early times it was small, late times it was bigger, and later times it was bigger. So the question is, how far do you have to run that movie backwards in time before it was all in one spot, before it was all at size 0? And you can estimate that, you would have a reasonable first guess for the age of the universe. Okay? Are there questions about that? So, let me talk about this in terms of an analogy. Okay? So, let's say you're at your house waiting for your friend to come over. Okay? And your friend's 10 minutes late. And finally he comes driving up in front of your house, driving 60 miles an hour, and stops. Okay? And he's like, sorry I'm late, And you're like, wait a second. You're supposed to be here 10 minutes ago, and you only live 10 miles away. So I know you probably left your house. You were already late when you left the house. Okay? And how do you estimate this, right? You know he lives 10 miles away. He drives up to your house going 60 miles an hour, and 60 miles an hour is a mile a minute. So driving a mile a minute, he lives 10 miles away. So, now most of you will just say, oh, okay, that probably took him 10 minutes. But then, the geeks among you, like me, would be like, oh, I can write an equation for this. The distance he travels is equal to the velocity he travels times the time. And I want to figure out how long he's been traveling t. So I can solve the equation. Okay, I'm all excited about that. Here's t. It equals the distance divided by v. So you have just divided both sides by v. The distance he traveled is 10 miles, and the speed he's traveling is 1 mile per minute. So 10 miles divided by 1 mile per minute. The miles cancel. The minute comes back up on top, and it's 10 minutes. All right? And you're like, aha, you were late. You were late before you left. Okay? So that's what we want to do here with the universe. We want to say, look, we know how fast you're moving now, and I know I want to go back to 0, and I want to figure out when you started. Okay? That's the estimate that we want to use. So let me just show you how to do this estimate. So remember, Hubble's law is the velocity equals h naught times the distance, where h is Hubble's constant, d is the distance, and v is the velocity. That's how fast you're moving. Now I can rearrange that equation. Okay? I can solve for d. I can say, look, the distance is equal to velocity divided by h naught. Does everyone see that? Are there questions about that algebra? Just taken h and divided both sides. Now remember the geeky equation that I used when I wanted to figure out when my friend left. Okay, I said, well, the distance is equal to velocity times the time. Now look at this equation and look at this equation. Do you notice any similarities? This is the distance equals the velocity times this distance. And this is the distance equals the velocity times time. So the time in here is playing exactly the same role as 1 over Hubble's constant. What this means is that I can associate 1 over Hubble's constant with the characteristic time. And in fact, Hubble's constant has units of 1 over time. So when I invert it, I have units of time. Are there questions about that? What I'm doing here? So what I'm saying is, let's assume the universe has always been expanding at the same rate, which is what you assume when your friend came to visit you. It's always been expanding at the same rate. It's always been expanding at the same way. That I can use this simple expression, the distance equals velocity times time, and figure out when the distance was 0. Okay? And it turns out that if we use the current estimate of what Hubble's constant is, which is 70 kilometers per second per megaparsec, which is units of 1 over time, the answer you get is about 14 billion years. And in fact, I'll show you how you work that out in a second. But does anyone have any questions about that? Like what I'm doing? Okay. Now, so this is an example of a units problem, actually. And this is a kind of units problem I'm going to expect you to do on the final, or the second midterm, whatever. Show that if h naught is 70 kilometers per second, then we have what we call the Hubble time. This 1 over h naught is called the Hubble time. Then 1 over h naught is equal to 14 billion years. How do we show that? Well, I'll show you how you do it. So this time that I'm looking for is 1 over h naught. And h naught is 70 kilometers per second per megaparsec. So how do I do that? So then I have to keep track of all the units here. All right? So if I have 1 over 70, then it's 1 over 70 there in the first term. Kilometers is in the numerator, so now it's in the denominator. And the seconds and the megaparsecs go up on the numerator. So it's 1 over 70 times megaparsecs divided by kilometers times seconds. So what I have to do is I have to convert megaparsecs, which is a unit of distance, into kilometers, cancel the kilometers out, and I'll get a unit, something in seconds. That's what's going on. Now a megaparsec, and I'll give you these numbers on the test, and you should have these written down somewhere. So all I have to do is plug 3 times 10 to the 19 kilometers in for megaparsecs here. And now I've got kilometers down here, and I've got kilometers here. And those are eventually going to cancel. Now, if I do this, I'm going to get a super big number, and the number is going to be in seconds. So instead of using seconds, I'm going to use years. Because years are, it won't be as many years as seconds, obviously. Now, there are about 3.15 times 10 to the 7 seconds in a year. So if I put that in, for how many seconds there are in a year, and I work all this business out, I get about 14 billion years. All right? So in the exponents, this is 19. I'm going to subtract 7. You're going to get something like 10 to the 12. And then there are other couple factors of 10 in there that give you 10 to the 10. Okay? So that's how you estimate. That's a first order estimate of the age of the universe. And Jinru will go over related problems in discussion section on Friday. Yeah?
So let's say we want to do this calculation a billion years from now. Would we use the same Hubble's constant? Because that would give us the same number.
Very good question. Very, very good question. I'm getting to that now. That's a great question. And the thing I'm getting to is, let's say I'm your friend, okay? Or not me, but someone much more lazy than me. And I show up at your house and I'm 10 minutes late. And you're like, no, you were late before you left, okay? It only takes you 10 minutes to get here and you're 10 minutes late. I know you were late before you left. And I'd be like, no. See, there's traffic, right? I'm stuck in traffic. See? So I'm stuck in traffic, And just because I was going 60 miles per hour when I came to your house doesn't mean I was going 60 miles an hour the whole time. In fact, I was speeding up the whole time. I was stopped dead for an hour, and then I sped up and tried to get here as soon as I could. That's the only reason why I'm late. Okay. All right. So you can check this. You can check it out because you can go on SigAlert and see what's in traffic. Right? I've been tracking SigAlert. I can tell you right now, you were not stuck in traffic. But that's the kind of, detective work you would have to do to really know the age of the universe. Has it been expanding at a constant rate the whole time? Has it been slowing down? Has it been speeding up? Okay? That's what you need to know the real age of the universe. So this thing that I've given you, this 14 billion years, it's a rough guess. If you had to guess how long it took your friend to get to your house, it'd be about 10 minutes. But it could be 4 hours. Or your friend could have driven like 1,000 miles an hour and then just slowed down right before he got to your house just to so you didn't think he was speeding or something. Okay? So in order to really know that, you have to know something about whether the thing is speeding up or slowing down. Now, for something that's expanding and also being affected by gravity, you got to know how much gravity is slowing this process down. So let me give you a different analogy. Let's say you were up on a ladder, okay, and a tennis ball comes flying up by you. It's this tennis ball I was talking about throwing up before. It comes up by you and it's traveling at some speed. 1 mile an hour comes by you, and you're a mile up. So you might think, oh, okay, well, it took an hour for that ball to come up this mile. It was going a mile an hour, and it's on a mile up, so it took about an hour. But is that a good assumption? Probably not, because the tennis ball has been slowing down, right? You throw a tennis ball up, it doesn't keep going the same speed. It slows down, it slows down, it slows down, it slows down. Eventually it turns around. It stops. Okay? So probably the question is then, well, did it take longer than an hour or shorter than an hour to get up here if it's been slowing down the whole time? Does anyone know? When it was first launched off the ground, was it going faster or slower? Faster. So if your person's coming to your house and at first they're driving really fast and then they drive slow, you're going to overestimate the time it took them to get there. Because at first they're making a great time and then they're making slower and slower time. So if the ball's been slowing down on its way up, okay, then it's actually going to have gotten there much in less time than an hour. Because at first it might have been going 100 miles an hour. Now it's only going 1 mile an hour. So it might have only taken a few minutes to get up here. See what I mean? But if we're super geeky and we know the mass of the Earth, and we know therefore how much the ball has been slowing down, we can calculate all this business. Okay, we know exactly if the ball is going this fast now, how fast it was going when it left, because we know how much it's been decelerating on the way up. We know the mass of the Earth, so we can do that. And so what I'm talking about is, this is the distance from the planet's surface, and this is how long the ball's been traveling. Okay? If there was no mass on the planet at all, the ball would just keep going straight. Right? But if there was more mass on the planet, that means it was going faster at first. That's a steeper slope on this plot. More distance per time. And then it's been slowing down since then. And if the planet's even more massive, it was going really fast when it was launched, and it's been slowing down a lot. All we know right now is how fast it's going right now. And how fast it's going right now is how far it's moving per time, and that's the slope of this line. Okay? Your calculus teacher would say it's the derivative of this line. It's the local speed. But it's just the slope. It's how fast it's going up compared to how much time it's going on. Is the speed. And at first it was going really fast, and now it's slowing down. In this case, in the red line case. In the case of the blue line, it hasn't been slowing down at all because there's no mass on the planet. The ball just keeps going straight. See what I mean? So this is what we can measure. How fast it's going now. And what we can infer is how much the line's been curving by knowing the mass of the planet. The more mass of the planet, the more it's been curving down, and therefore the less amount of time it's been traveling. So this is when it left the ground. A less massive planet would have been traveling for longer, and a massive planet would have been traveling for the longest amount of time. And that's the assumption of not slowing down. Now, this is the assumption we've made in doing this Hubble time calculation. We've been assuming that the universe looks like this. But if there's stuff in the universe, then these lines are going to curve. So that's how it works. If we knew the mass density of the universe, if we knew how much mass there was per unit volume in the universe, we could figure out how these lines curve. And then we could go from how long has it been from today back to the time when the universe had 0 size. Okay? So for example, in the case of the purple line, this would be the age of the universe, and this blue would be the Hubble time, this 14 billion years. So the more stuff there is in the universe, we would expect, naively then, that the universe is going to be younger and younger and younger. Because it's been slowing down a lot. Any questions about this? Okay. Now, so if we add up all the matter in the universe, including the dark matter that I've talked about, it's not quite big enough such that this line is eventually going to turn around and come back to 0. Okay? Because if the planet's massive enough, right, the tennis ball is going to go up and eventually come back down and crash. If the universe just has enough mass density, then the universe is going to expand to some point and then recollapse on itself. And this is called the Big Crunch. It's the Big Bang, and it's the Big Crunch. If there's not as much mass as that, then the universe will just keep expanding forever. That tennis ball is launched off the surface of the Earth and never comes back. And right now, if we add up all the mass we know about, it's something closer to this purple, in between the purple line and the blue line, is that the universe is going to keep expanding. Okay. Now, how does Hubble's constant come into this? Well, Hubble's constant is basically the slope of this line. Okay, because it's how fast things are moving at a given distance. And so if Hubble's constant goes up, then all the slopes go up. See what I mean? But all this thing just tilts. So all the times get shorter. If Hubble's constant goes down, it's the other way around. All the times get longer and extended. This is another one of these diagrams that took me like 3 hours. So I got to show it, keep showing it here. Okay, so that's why we want to measure Hubble's constant. That's why we want to. Okay, so now, that's why this Hubble's constant is so important, right? That's why That's why this Hubble's constant is a very important number because it's fundamentally linked to how you normalize the age of the universe. It's this fundamental thing that tells us how old the universe is, right? And a lot of people don't know this, but the key project for the Hubble Space Telescope, you could argue it's the main thing the Hubble Space Telescope was built to do originally, was to measure this, was to measure Hubble's constant. And, I mean, it was built for other reasons, but this was one of the main things that it was built to do. And Hubble finally did it, and with the help of Hubble and a few subsequent observations, we now have a very good understanding of what h0 is, what this Hubble constant is, and it's, like I said, around 70 kilometers per second per megaparsec. Okay. Now, this turns out to be very weird. Because you take Hubble's constant, and you determine the Hubble time, and you get an answer that's something like 13.9 billion years. Which means even if the universe doesn't have any matter in it at all, if it's not slowing down at all, the universe is 13.9 billion years old. So you might think that's an upper limit for how old the universe could possibly be. And that's crazy, because we know the universe should be slowing down a little bit, because there's mass in the universe. The problem is that if you look at the ages of the oldest stars and these nearby star clusters, the globular clusters that I talked to you about, they are almost this old. Which suggests that naively you would think that that means there's stars in the universe that are older than the universe, which doesn't make sense. So there's some problem here, because we have a really good understanding of how fast the universe is expanding. In absence of all slowdown, it maximally can be about 13.9 billion years old, and we have stars that are almost that old that we can see. So in the late 90s, this was considered a big crisis. Okay? Not because it was on the cover of Discover magazine, but I just figured I'd put it there anyway. You know, proof in journalism. But here's the weird thing, okay? So after these astronomers stopped reading about the giant sperm, they figured, well, we got to get to the bottom of this. And in 1998, astronomers did a different experiment, and they actually went out, because if you can see objects that are really far away, you're looking back in time. So if you study how fast objects are receding from us that are really, really far away, so far away that it was effectively going this way in the diagram, they discovered something fascinating. That in the past, the universe was actually expanding at a slower rate than it's expanding now. It's as if that tennis ball went up and just shot up and accelerated in midair. Like it had a little rocket pack on it and just launched up. Which is super weird. Super duper weird. But it's as if what this diagram is doing is it's doing this, almost like there's anti-gravity. But this is what we see. We measure, this is what's happening to the galaxies as they expand away from each other. This effect, this anti-gravity, okay, the fact that this is going on, first of all, solves this age problem. Because it gives us this extra boost. The fact that we're actually going a little bit faster now than we were in the past gives us more time and solves this age problem. And the thing that we think is causing this expansion, this accelerated expansion, is something we have no idea what the hell it is. But we gave it a name, so it has a name. Okay? So you just name it and then it's all good. What we named it is dark energy. So this stuff is called dark energy. So if you've heard of dark energy before, that's what this is. It's whatever the heck it is that's making the universe accelerate. I'm not going to talk much about exactly how this was done. The way astronomers determined the distances and speeds to very different objects was kind of like the same way we did with standard candles with Cepheids, except we need an even brighter candle, and the candle that was used was supernova. So supernova are like the brightest explosions in the universe, and it turns out supernova can be used as standard candles. And once this was realized, then there was a team at Berkeley and a team at Harvard that did this experiment and showed that the universe is accelerating and discovered this dark energy. If you recall, way back when Einstein first did general relativity, someone pointed out to him that the universe should be changing. And Einstein said, oh, I can fix that. All I have to do is add a term in my equations that acts as an anti-gravity that stabilizes the universe. This is called the cosmological constant. It turns out that if you take that cosmological constant and just put it on the other side of the equation, it does exactly this. It makes the universe accelerate in its expansion. Okay, so it acts as an anti-gravity and makes space want to expand apart, growing and growing with time. So this dark energy, it doesn't shine, it causes the universe to accelerate, and we have no idea what it is. The most prominent idea right now, the most common idea for what this is actually Einstein's old cosmological constant. So it could be that Einstein's greatest blunder was actually his greatest triumph in the end. That by accident, he predicted the existence of this accelerating stuff, this dark energy that pervades the universe. There's other ideas that effectively it's like another force of nature that we've just discovered. And the final possibility is just that we don't understand Einstein's general theory of relativity, and there's some deeper, grander theory of gravity that we're seeing evidence of. It turns out it's not obviously this. This is very, very hard to make anything else work besides Einstein's general relativity that doesn't screw up everything else. Like, if you try to fiddle with this model, it just screws everything else up, like the orbits of the planets and other stuff we really understand. So really interestingly, this is the leading model right now, which, poor Einstein just had no success as a scientist. Okay, that's it. Remember, no lecture on Tuesday, and we'll see you in about a week.
Yeah, exactly.
Oh, yeah.